Okay, so thank you everyone for tuning in to the inaugural Quantum Gravity and Information Seminar Series. The first one is given by Daniel Harlow at MIT. These are interactive. Please feel free to interrupt and ask questions. So yeah, Daniel, thank you very much, and take it away.
Okay, so I'm going to talk about a paper that I wrote last summer with Jae-Chang Wu, who is a postdoc here at MIT. Maybe some of you know him. Smart guy. So our paper was called Covariant Phase Space with Boundaries, and it grew out of my own efforts to try to understand how to think about quantum information-y kind of concepts in general relativity, things like the commutators of operators and Hamiltonian evolution of gauge invariant operators. So these are things which, from the boundary point of view, are quite natural, just doing Hamiltonian quantum mechanics. But it's, as you know, if you've tried, let's say, not easy to do a Hamiltonian formulation of gravitational theory. And in particular, in the standard way of doing it, which is the ADM formalism, you have to mutilate the covariance of the theory by introducing a foliation and then talking about the lapse and the shift. The equations get rather complicated. And in fact, I would say that even until the mid-90s, there was no really correct analysis of the Hamiltonian formulation of general relativity. There was always some guesswork involved. And then finally, in the mid-90s, there was a paper by Hawking and Horowitz, who showed how to really do the Legendre transformation from the from the Lagrangian to the Hamiltonian, being careful about everything that you need to be careful about. And the key issue that people were not careful about in the past was boundary terms. Now, usually boundary terms are something that we just kind of ignore or don't think too carefully about because, if you're in the middle of the space, who cares what's going on out at the boundary? But when you're trying to set up a Hamiltonian formulation of the whole theory, it does matter what's going on out at the boundary because that's part of the system. And it especially matters in gravity because actually the Hamiltonian is a boundary term. So if you're not familiar with that, it's basically a consequence of diffeomorphism invariance. And it's analogous to the statement that in electromagnetism, the correct definition of the electric charge is that you measure the electric flux at infinity. So since the U1 gauge transformations are gauge transformations, the consequence of that is that the generator of the gauge transformations is this flux that lives at infinity. And so the same should be true for energy and momentum and so on in gravity. So then if you're trying to do a calculation where the answer is a boundary term, then you'd probably better be careful about the boundary terms. It seems obvious, but actually that was not the philosophy in the literature for the first 40 years of the subject, where people would just kind of follow their nose and then run into some thing where they need to make up some boundary term to solve it and then sort of try to guess. Now, in the early 90s, in the 90s, there was two kinds of progress on this front. One was this paper I mentioned of Hawking and Horowitz, which within general relativity, they showed how to be careful about the boundary terms in constructing the Hamiltonian, but using non-covariant methods. The other advance was in these papers, the famous papers of Iyer-Wald. Is someone asking a question? I saw someone flashed up here, but I can't hear if anyone was asking a question. So, okay. So there are these famous papers of Iyer-Wald where they showed how to do a covariant version of the Hamiltonian formalism that doesn't require you to pick a foliation or talk about the lapse and the shift or do anything else that breaks covariance. And well, clearly that's going to be a good thing if you can do it because general relativity is covariant. And so if you can do all the calculations, with 4 vectors and tensors and so on, instead of having to decompose, then the calculations are going to be easier. But if any of you have studied the Iyer-Wald formalism, you probably noticed that they're not careful about the boundary conditions and about the boundary terms. And then again, you're back into this soup of like, the answer for everything interesting is going to be a boundary term, but then you're not keeping track of boundary terms, so you have to do some inspired guessing here and there and kind of hoping that there exists something with some property, and then only afterwards can you, for example, write down a formula for the Hamiltonian. So Jae-Chang and I were trying to learn this Iyer-Wald formalism, and we were just getting frustrated with these boundary terms. And so we decided that the only thing to do is to just reinvent everything from the ground up, being careful about the boundary terms. So the result is a formalism where, for any theory that you want, it's essentially trivial to write down the Hamiltonian. For example, we can derive the ADM Hamiltonian of general relativity in just a few lines of algebra without any guesswork. And actually in our paper, you can compare. So we do a version of the Hawking and Horowitz calculation in the appendix of the ADM Hamiltonian. And you can see that it's just a lot more algebra than it is if you do it using the covariant method. And also then, although I probably won't have time to talk about it, we explained how within the covariant formalism, you can compute the commutators of gauge invariant operators without ever having to break covariance. And so in particular, I don't know how many of you ever suffered through this, but the old-fashioned way of computing commutators in gravity or in gauge theory is by using Dirac brackets, which are not pleasant objects to use. Dirac brackets, well, you have to pick a gauge, and then you have to turn all the first-class constraints into second-class constraints. You have to compute a matrix of the commutators of the constraints. You have to invert the matrix, and then there's some expression that you use in terms of that inverse to compute the commutators. So in the covariant formalism, you never have to pick a gauge. You never have to invert a matrix. There's just a systematic procedure of computing the commutators, which is called the parallels bracket, which never requires you to do anything non-covariant. So if you like this as kind of a formalism talk, there are a few, there's some old puzzles in the literature that I think we clarified a little bit, but mostly this is about developing something that then you can use to explore whatever sort of algebraic questions you might be interested in a gravitational system. So just to make sure everyone's still on board, I'm not talking out into space, right? Because I can't hear if you're all still hearing me.
And we're still here in Potsdam. I don't know.
We're here in Amsterdam.
Okay, very good. Just making sure. So is there any question about this sort of general philosophical thing, or I started explaining what is this covariant phase space formalism?
No questions here. If anyone does have a question, feel free to just unmute your mic and speak up.
Yeah, you can just shout it out. I don't, it should be informal.
Yeah.
Okay, so let me begin by reminding you what we mean when we talk about a Hamiltonian formulation of mechanics. So what you learn in class, as an undergraduate or whatever, is that you have a phase space with coordinates q and a and pa. And then you like to talk about Hamilton's equation of motion. Q dot A is dH dPA, and P dot A is minus dH dQA. Now, if we're going to try and do things this way, it's just never going to be covariant because P is defined, if you like, as dL dQ dot, and you have to say what dot is, right? To define dot, you have to pick some time slicing, and then things are going to be defined relative to that time slicing. So we don't want to do Hamiltonian mechanics this way. So the standard way of fixing that is that you say that instead of talking about this particular set of coordinates, you just say that you have a phase space, which is an abstract manifold P, which labels the, if you like, the set of initial conditions of the theory. The set of, or if you like, the set of histories, since those should be in one-to-one correspondence. And then you just say that, okay, so if you pick some particular Q and P, that's like picking coordinates on this manifold. But then if you pick like the P from a different time slicing, you're just picking a different set of coordinates on the same manifold. So if we just talk about the manifold, then we don't have to make that split into Q and P. But then you can ask, okay, well, still we have to know how to say what the dynamics are, right? So the idea is that dynamics will be described by giving curves in this phase space P that tell you how the system moves from one point in phase space to the other as you evolve in time. Let me think of how to say this. So the key point of the abstract formulation of Hamiltonian mechanics is that not only do you have this phase space P, but actually it's a symplectic manifold. So living on it, you have a symplectic form. So the symplectic form is a closed 2 form. So d omega is 0. And it's also non-degenerate, which means that there aren't any vectors that it annihilates. And then the idea is that what is the symplectic form good for? Well, what it's good for is that it turns a function on P into a vector on P. So let me see if I can say how that works. So the idea is that, like, say that H is some function that sends P space to the real numbers. So it's like a candidate Hamiltonian. And then given this function, we want to turn it into a flow on P. So geometrically, if we didn't have this omega, there wouldn't be a natural way to do that, right? Like if I just come to you with a function, on a scalar function on a manifold, there's no natural way of constructing a vector. There is, however, a natural way of constructing a one form, which is that we just take the gradient or the exterior derivative. So given this, I can define a gradient, which I'm going to write for reasons that will be clear later as delta H. So this delta means the exterior derivative on phase space. I call it delta because later we're also going to have exterior derivative on space-time. And so we need to be clear about which exterior derivative we're talking about. So delta is the exterior derivative on phase space. So given H, I can turn it into a one form. But then the idea is that to get a vector field, I have to somehow raise the index of the one form. So that's what the symplectic form is good for. That's its purpose in life. So the idea is that given H, I can define a vector field, which I'll call XH, where being a little bit careless about the sign, since the details don't matter for this talk, what we do is we take omega inverse and then act on delta H. So you can say, what is this omega inverse? Well, that was where the fact that omega was non-degenerate was important. So since omega is non-degenerate, so omega is a 2 form, but I can turn it into a 2 vector. Since it's non-degenerate, I just, in whatever coordinates, I take the inverse of omega. And then the inverse of omega is a 2 vector, so it's something that eats a 1 form and turns it into a vector. Now, finally, once you have a vector on phase space, then that's the same thing as having dynamics, because then you can just say, like, say I have some other function f from the phase space to r, and I want to know how f changes with a function of time. So the idea is that I just take the vector field and I act with it on f. So that's what a geometer would say. If you want me to write it in index notation, it's something like xh mu d mu f. Okay? And that's the definition of the time. That gives a time evolution of any function. And actually, if you then decide, like for this example, in this example, you just say that omega is dpa wedge dqa, sum on a, and you use this formula, this geometric formula for the evolution, then you get back to this Hamilton's equations of motion. But you see, now we've formulated Hamiltonian mechanics in a coordinate-independent way. You just have a phase space manifold P. You have a symplectic form omega, which is closed and non-degenerate. And then that allows you to turn any function on the phase space into a Hamiltonian, in the sense that it allows you to turn it into a vector field. And the integral curves of that vector field are the evolution of the system. Okay, any questions about that? Hopefully that's somewhat familiar. Or at least you heard it once before. Okay, you're also quiet. All right. Now, let's think a little bit more about the definition of phase space. So, to realize this formalism, we have to take some mechanical system and identify what is the phase space. So the traditional way of thinking about that is that you say that the phase space is the set of initial conditions on a time slice. Right? So like, for example, if we have a single particle, then we have Q and P, or Q and Q dot at time t equals 0, and that parameterizes the phase space. But that's still not very covariant, right? Because we had to pick this time slice that we're going to use. And then we use the initial data on that time slice. So a more natural proposal, which I think it has a long history. I'm not totally sure how the details of the history, but at least in the 80s, there was a paper by Ed, Winin, and Chernkovich, which suggested this. So the idea is that instead of labeling the phase space by the set of initial data on time slice, you label it by the set of solutions of the equations of motion of the system. So if the initial value problem is well posed, then the set of initial conditions on any time slice should be in a one-to-one correspondence with the set of solutions of the equations of motion. But the latter is a completely covariant thing, right? Like I just say the set of solutions of equations of motion. I don't have to pick a time slice to say that. So the main idea of covariant phase space is to try to define P as the set of solutions of the equations of motion. Now, in theories with gauge symmetry, though, there's a problem with this. So, okay, let's make this more participatory. So what's the problem if there's gauge symmetry? Anyone want to volunteer?
Symplectic form should be generic, right?
Can you speak up? Sorry,
The symplectic form should be generic.
Yeah, but more intuitively, why should that be the case, right? Like say in electrodynamics. Well, the problem is that you can do gauge transformations that are a function of time. So, like say here's some initial slice where I specify, the electric, A and B and the electric field and whatever else I want to specify here on this time slice. I can always do a gauge transformation which vanishes in a neighborhood, an open neighborhood of this time slice, but then is non-vanishing up here or down there. Okay. So what that means is that the set of solutions is not in one-to-one correspondence with the set of initial conditions. Because if I do that gauge transformation, I can send one solution to another solution, but they have the same initial data. So this is like the sort of fundamental problem in gauge theories, right? Like it means that the dynamics is not well posed. And so the only way to deal with that is to say that you have to identify solutions which differ only by a gauge transformation. Now, even that is, you have to be a little bit careful, because really there will be some subset of the gauge transformations which you quotient by. And a lot of the business is knowing which subset to quotient by and which one not to. So let me see if I can say this in a good way. And in fact, it was suggested already. So let's start by considering the set of all solutions. So I'm going to give that a name. I'm going to call that P tilde. So, well, that's a symbol, but then I'm also going to give it a name. It's called pre-phase space. And this is just the set of solutions. And this is solution. If there's a boundary, then it's a set of solutions that obey the boundary conditions. So I'm going to show you in a little bit that for any Lagrangian field theory, there's this pre-phase space that we can construct. It's just the set of all solutions. And then there's also going to be a natural construction of something called omega tilde, which is called the Pre Symplectic Form. And so I'll write down the formula for it in a little bit. It'll be some natural 2 form on P tilde, which will be closed. But it may or may not be non-degenerate. And in fact, as was suggested, whenever there is a gauge symmetry that leads to an ambiguity in the solution of the equation of motion, at least if it's a continuous gauge transformation, then there will be a 0 mode of this pre-symplectic form. And that kind of has to be the case, right? Because remember, if this pre-symplectic form, if it's non-degenerate, then the dynamics is unique. We can just do this construction. We invert it, we get a vector on the phase space, and then that gives us a unique evolution. So this phenomenon of the evolution not being unique is directly related to this question of whether or not there are 0 modes of the pre-symplectic form. Okay?
I have a question. Can you hear me?
Yeah. Hi, is that Alex?
Yeah. Hi, Dan. So what you described is very well suited for systems that have second order dynamics. So where the differential equations are second order.
Yeah.
Does it work in general if you have higher,
Yes, it works with no difference. So the formalism that I'm going to present is going to work for any finite number of derivatives. And in fact, with any finite number of derivatives, there's still the Hamiltonian formalism in the abstract way that I said looks exactly the same. You have a phase space, you have a symplectic form, and you use it to generate evolution. The only thing that's different is that you don't have this natural split of the coordinates into Q and dl to Q dot. There's kind of more coordinates that come from derivatives of the Lagrangian with respect to higher time derivatives. But since I'm not going to do that, since I'm doing everything covariantly, it's all going to just be the same, whether or not they're higher derivatives.
Okay, thanks.
Okay, so now let me just say, so sorry, this first part, there's kind of a decent bit of differential geometry that I just have to throw at you. So these 0 modes, so the 0 modes of the pre-symplectic form on pre-phase space are vector fields, right? Because this is a 2 form. So 0 modes will be vector fields. And you can show that the Lie bracket or the commutator of 2 0 modes always gives you another 0 mode. So that means that the 0 modes of omega tilde generate a Lie algebra. And you can think of that Lie algebra, you can then exponentiate it to get a group that acts on P tilde. And if you like, that's what you might call the gauge group. It's a set of transformations of P tilde, which are generated by the 0 modes of omega tilde. So let me call that G tilde, which is the group generated by 0 modes of omega tilde. Okay. And then finally, the idea is that to construct the actual phase space, the one where the evolution is unique, we just start with the pre-phase space, P tilde, and then we quotient by G tilde. So that was the proposal of Trinkovich and Witten. So that kind of tells you, well, so sorry, let me say a little more carefully. So at least for continuous gauge symmetries, this is like a unique specification of which gauge transformations you're supposed to quotient by. The discrete case is a little more subtle, but maybe I won't discuss it here. Okay, so that's kind of the formal machinery. Oh, let me also say, maybe I won't explain it explicitly, but so then so this constructs the phase space P. I also want to construct the symplectic form. So the idea is that to compute the symplectic form acting on two phase space vectors, what you're supposed to do is take the pre-symplectic form and then use like the push forwards of those vectors through the quotient map to define the symplectic form. And it's in the paper, maybe I won't go into detail. You can show that this is well defined and unambiguous and also non-degenerate. But it kind of makes sense it should be non-degenerate because we quotiented by all the zero modes, right? All right, so that's it for the kind of general formalism. Any questions about this, or now we'll try to make it more concrete? I mean, somehow to make this real, what I have to do is give you an algorithm given in action for constructing this omega tilde and this the p tilde, right? And then eventually also the Hamiltonian. Okay, so I'm going to erase this.
Hello, can I ask a question?
What is the question?
Yeah. You briefly mentioned something about the discrete symmetries.
Can you speak up a little bit?
Oh, sorry. I don't know where the mic is. You said something about the discrete symmetries or gauge symmetries.
Yeah. Is that Anthony?
Yeah.
Hi, Anthony.
Is there a different procedure? Because you said there was some subtlety.
Yeah, well, the subtlety is that you can't decide which discrete gauge symmetries to quotient by just by looking at the symplectic form, because they don't correspond to zero modes of the symplectic form. And discrete invariance of the symplectic form is fine. There's nothing sick about that. So that you kind of have to deal with. You can't deal with it at this very high level. You have to actually look at the Lagrangian system that you're studying. Basically, I mean, roughly speaking, you want to quotient by the ones that sort of vanish near any boundaries. But to have ones that are non-trivial but vanish at the boundaries, you need some topological, the space needs to be topologically non-trivial in some way.
Okay.
So what you really, I mean, the principle that really tells you there, yeah, let me say it in a different way. So the principle that tells you which discrete symmetries to gauge is the principle of spatial locality. But spatial locality is something that you kind of don't see at this very high level because we're just talking about the time dynamic. I mean, from this point of view, there's no spatial locality, right? We're just talking about general mechanical systems. So that's already enough to identify the continuous gauge symmetries, but not the discrete ones. You have to put in some axioms of quantum field theory to identify those.
Okay.
Okay.
Thanks.
Yeah. Any other questions? Okay. Okay. Let me now erase everything. Okay. So now let's talk about local Lagrangians. So I'm going to adopt this convention of Wald that when we talk about Lagrangian, we're talking about D-forms instead of Lagrangian densities. So for me, a quantum field theory, well, not quantum, everything is classical, a classical field theory, we'll describe it by saying that we have an integral over M, which is the space-time manifold, which for me is always Lorentzian, of a D form L, plus an integral over the boundary of M of a d-1 form little l. These Lagrangian forms can depend both on dynamical fields, which I'll call phi, and background fields, which I'll call chi. So, for example, for a scalar field theory, we could have that L is minus 1/2 d mu phi g mu nu plus v of phi times epsilon. Where here phi is the dynamical field, g is the background metric, which is not dynamical, and epsilon is the volume form, because L should be a D form. Now, in the formalism of Iyer-Wald, this L is viewed, this big L is viewed as ambiguous up to adding a total derivative. I don't view it as ambiguous because I'm explicitly including a boundary term in the action. So if you add a total derivative to big L, you change little l. Well, unless the thing you add vanishes at the boundary, and if it vanishes at the boundary, it doesn't do anything, so let's forget about it. Now, the basic idea of Lagrangian mechanics is that we want to look for configurations of the dynamical fields such that, well, roughly speaking, we want to say that S is stationary about those configurations under all variations of the dynamical fields which obey the boundary conditions. But actually, that's not quite right. So let me draw a little bit more carefully. So let's say this is M. I'm going to split the boundary of M up into 3 parts. There will be a future boundary, sigma plus, a past boundary, sigma minus, and then a spatial boundary, gamma. So for this talk in this paper, I'm not going to discuss null boundaries. It's not necessarily because I don't think they're important, it's just that I think they're confusing. It would be interesting and I think maybe important to generalize what we say here to null boundaries, but I'm not going to do it. I guess I spent too much time living in ADS. So then what you really want to say when you say that the action is stationary, what do you really mean? Well, I would say what you really mean is that if you compute the variation of S, you get, and you evaluate at a configuration phi, which we're going to want to eventually be a solution, you know, a meaningful history, we want to get the integral over sigma plus of some local functional psi minus the integral over sigma minus of the same local functional. Now, you might say that that doesn't look stationary. And it's true, that's not, you know, stationary would be I would put 0 on the right-hand side. But the thing is that when I talk about the set of solutions, it's very important that I don't want to impose boundary conditions in the future and the past. Because boundary conditions in the future and the past tell you what state you're talking about, right? So when you're talking about the theory, you don't want to specify the state. So I'm going to only want to impose boundary conditions at the spatial boundary, because that's part of saying what theory you have. But imposing them here, that would be too much. Like if I impose boundary conditions here and here, then if I'm lucky, there will be one solution, and there may not be any. Okay. So I want to consider variations which preserve the boundary conditions here, but which are arbitrary in the future and the past. And then the best I can get is that the variation of the action will just give me a term here and a term here and nothing else. Okay. Now, let's see if that's actually true by computing the variation of the action. So to compute the variation of the action, there's a nice formula that we can use. So for any Lagrangian form, by doing kind of integration by parts kind of manipulations, you can show that, you can see the bottom here if I write here, right? Yeah, I think it looks like you should be able to.
Yep. Yeah. We can see it here.
Yeah, okay. I guess the Amsterdam were the ones who are causing the trouble, but it's okay in Amsterdam?
Yeah, we're good.
All right, great. Okay. So we can, in computing the variation of the Lagrangian form, you can always rewrite it in the form where you have some EA, depending on phi and chi, times delta phi A, plus D of some theta, which is a D minus 2 form. Sorry, D minus 1 form, which also depends on phi and chi. So the idea here is just that you, in general, when you compute the variation of the action, there will be derivatives acting on the dynamical fields, right? Like, for example, for this action, there will be a term with a derivative acting on the dynamical fields. But then this is just the thing we've been doing since undergraduate, right? Then you just kind of integrate by parts, not quite because you're not doing the integral yet, but you just write it as a total derivative plus something where there's no derivative acting on the variation. So by doing that, you're going to show that the variation of L, there'll be a unique term where there's a delta phi with no derivatives, and then there will be D of this theta. And this theta is called the symplectic potential. So, well, okay, I'll just say it. It's called the symplectic potential. Okay, so using this, we can now compute the variation of the action. So the variation of S, so there'll be an integral over the interior of M of this EA delta phi A. And then there'll be an integral over the boundary of M of theta plus the variation of L. Okay? So I just, I used Stokes Theorem here. So I did the variation of L, and then there was D of theta here, and so then I moved theta out here to a boundary term. Okay? Now, let's think about what would need to be true in order that the variation of the action would have this form here, which is the form that we want. Well, the first thing is that this EA is going to have to be 0, because we can vary the dynamical fields independently at every point in the space. This is what we learned as undergraduates. So the first thing we learn is that EA has to be 0. And that makes sense because these are just the equations of motion, right? So that's not very controversial. Okay. But even after we did that, we still don't have this form because we have a boundary term, but in general, this could have support here on this spatial boundaries, right? And so the variation wouldn't be just in the future and the past. So to get rid of that, we need to have, well, you might say, so let's study the restriction of this to the spatial boundary. So if this is non-zero up here, that's fine, because that'll just be part of this side. But at the spatial boundary, this is going to need to be constrained. So your first guess, maybe, is that it should be 0. That would certainly work if this was equal to 0, and sometimes it is. But it's not the only thing that would work. In fact, something more general that would also work, and which could and does happen, is that this is just equal to D of a 2 form C on the spatial boundary, okay? Because if this is true, right, then I put DC here, and then at least on the spatial boundary part of this integral, and then that just kicks me up to terms which live at the corners here, and those are part of sigma plus and sigma minus. So this is going to be like our main equation, is this. The claim is that in order to have a consistent Lagrangian formulation of the system, and so far we're just doing Lagrangian, we haven't done any Hamiltonian, we need that the L appearing here and the theta that comes out here, when I move them to the boundary, they must be equal to d of c, where c is some locally constructed d minus 2 form. And I'll give an example in a little bit of this c so that it looks a little more concrete. Okay, so is there any question about that? All right. Now I want to make this Hamiltonian. So the defining the pre-phase space.
Sorry, question. Just
yeah,
theta depends on delta phi, right?
Theta depends on delta phi, yeah, and also its derivatives in general.
Right, right.
Yeah, but it's a if you like, it's a homogeneous function of delta phi. So every term in theta has exactly one delta phi, possibly with some derivatives.
Thanks.
Yeah. Okay. Now to define the pre-phase space, now we just say that we impose boundary conditions at gamma. And let me emphasize, this only needs to be true for variations that obey the boundary conditions. We don't care about variations that don't obey the boundary conditions. So then the claim is that the pre-phase space we will take as the set of dynamical field configurations which obey the equations of motion and obey the boundary conditions. And then if we've correctly set up the problem, then if we look at variations around those, this will always be satisfied for any variation that obeys the boundary conditions. Okay, so that defines the pre-phase space. We also now have to define the pre-symplectic form. So to define the pre-symplectic form, I first want to make a notational aside, which has to do with the meaning of this symbol delta phi a. So far, maybe you've been thinking about this the way that we think about it when we first learn about it, which is that this is like an infinitesimal function, an infinitesimal deformation of the field configuration phi. But actually, it's much, much better to think about this as a one form on the set of configurations of phi. So let me try to say this a little bit more carefully. So I want to define a big space C, script C, which is the set of all configurations of phi which obey the boundary conditions. But they may not be solutions of the equations of motion. And then living inside of this C, there is this P tilde, which is the set of configurations of phi which also obey the equations of motion. Then what I want to say is that I want to interpret this delta phi as a one form on the set of configurations. Right? So you should think about this morally as being like, in ordinary differential geometry, you write dxa, and that's a one form. It's like a coordinate differential on a manifold. So here, this is a coordinate differential on the set of configurations phi. So with that convention, we see that we can now think of theta, which, as we discussed, is something that's homogeneous in delta phi. We can think of theta as a differential form now in two different ways. We can say that it's a d-1 form on space-time, but we can also say that it's a one form on the space of configurations. So let me just pause there so you can think about that. So again, we're interpreting delta phi now as a one form on the set of configurations. Theta is a one form on the set of configurations. EA is a zero form on the set of configurations, but it's a D form on space-time. And so from now on, every object that we're going to talk about pretty much is going to be a differential form in two different ways. It'll be a differential form on space-time, and it'll be a differential form on the set of configurations. then any differential form on the set of configurations, it can then be pulled back to a differential form on pre-phase space, which is like a submanifold of the set of configurations. Okay. And so that's why we're really going to have to be careful. And then this delta here, right, now we can interpret it as the exterior derivative on a set of configurations. So that's like what I was saying before. So then from now on, whenever I write this delta, you shouldn't think of it as a variation anymore. You should think of it as an exterior derivative. Okay. End of notational tangent. By the way, somehow, for some reason, Iyer-Wald don't want to do that notational replacement, and then every formula, then every formula is more annoying because of it. So I don't know why they didn't do it. Okay, now let me give the definition of the symplectic form. So I'm going to do it in the following way. So I'm first going to define a pre-symplectic current, little omega, which I define as the exterior derivative of theta minus dc evaluated on pre-phase space. So that's a pullback, if you like. So here this new notation is very important because theta is a one form on pre-phase space. And you see here, C is also going to be a one form on pre-phase space. And so here I'm taking the exterior derivative again. So omega is a two form on pre-phase space. It's also a d-1 form on space-time because theta was a d-1 form on space-time and C was a d-2 form. And then I took its space-time exterior derivative. Okay, and so like half of this business is just keeping which exterior derivative you're talking about straight. Okay. So let me make a few comments about little omega. So the first is that little omega is obviously closed as a two form in phase space because it's already delta of something. So delta of it is 0. So delta omega equals 0, obvious. What's maybe less obvious is that omega is also closed as a d-1 form on space-time. So let's work that out. So let's compute d of omega. Am I writing too small, by the way? So
no, it's fine for us, I think.
It's fine for you? Okay. So let's compute d of omega. Well, so d and delta are commuting operations because they're like exterior derivatives on different indices. So the d will just go right through here and kill that d. So then I just get delta d of theta, okay? But d theta is just equal to delta of L minus EA delta phi A from this equation. And then so delta squared on L is 0. And then here when I do delta, I have to distribute the exterior derivative over the product. So when it acts on the delta phi, I again get delta squared equals 0. So I just get delta EA, delta phi A. And so then since we're restricting to pre-phase space, and E is 0 everywhere on pre-phase space, this is 0. Okay. So that's the kind of calculation which is very easy using this differential form technology, and if you don't, it's kind of so that shows us that omega is closed in space-time. Finally, and then I'm going to erase everything, so I want to fit it in here. This tiny board is hurting me. Finally, I want to say that the pullback of omega to the spatial boundary is 0. So that's going to follow from this equation, right? Because, well, I can rewrite this as delta of theta plus delta L minus dc. You're just using the delta squared on little l is 0, but then this is 0 on gamma by this equation. Okay, So we've learned that this pre-symplectic current has the property that its pullback to the spatial boundary is 0. We've learned that it's closed in space-time and also that it's closed in pre-phase space. All right, now here's the moment of glory. We can introduce the pre-symplectic form. So omega tilde, the pre-symplectic form, we will just take to be the integral over any Cauchy slice sigma of this pre-symplectic current. Now, to convince you that this is a good definition, I have to convince you of several things. The first is that this is independent of the choice of Cauchy slice that we make. That had better be true because the whole point is to be covariant. And so if this depends on a Cauchy slice, that would just be a pity. But in fact, it is going to be independent because if you think about it, right, like we can use Stokes theorem to write the difference between these two as the integral of d omega over the interior plus the integral of omega over these boundaries. But d omega equals 0, and the pullback of omega to gamma also equals 0. That was the discussion we just had. So this is independent of the choice of sigma. All right? So that's nice property number 1. Nice property number 2 is that this is a closed form on pre-phase space. And that's just because omega was delta of something. And so this is also delta of something. And so it's closed. So this is a good pre-symplectic form. It's independent of sigma, and it's a closed form. It may or may not be non-degenerate. If it's degenerate, then we have to quotient by the 0 modes, as we discussed before. Okay. So that's kind of it for the covariant phase space construction, at least as for in terms of constructing the pre-phase space, the pre-symplectic form. We do the quotient to get the symplectic form. Okay. So that's like that's like half of the Hamiltonian formalism. The other half is to find the Hamiltonian. But before we do that, let me stop and ask, are there any questions about this? By the way, when is my hour supposed to end? Because we started late.
Yeah, you've still got another five or so minutes based on when we started. But it's
5 minutes. Okay. Well, that's that'll okay. If we're serious about the 5 minutes, let me think.
Yeah, I mean, it's a soft limit if you've got, you know.
Yeah, I should at least say a little bit about the Hamiltonian.
Sure.
So and then I was gonna write out what the things are like for general relativity, just so that these symbols don't look so abstract. I could probably do both of those things in like 10 minutes.
That's fine with us. No one's going to kick us out of the virtual room.
Yeah, okay. So there's a whole discussion about, so far this is completely general, right? We could be talking about, you know, classical field theory, we could be doing electromagnetism, right, or scalar field theory, or we could be doing gravity. And for example, if we're just doing scalar field theory, it better not be the case that the Hamiltonian is a boundary term, right? Whereas if we're doing gravity, it better be the case that it is. So the difference between the two has to do with to what extent the Lagrangian is covariant. So what does it mean for a Lagrangian to be covariant? Well, let me first remind you that if C is a vector field that generates an infinitesimal diffeomorphism, then the transformation of any dynamical field is just the Lie derivative. Okay, here I'm assuming all the dynamical fields are tensors, or maybe tensor densities. So then we can define a vector xc, which is a vector on pre-phase space, or even a vector on configuration space, Let me write this correctly. Okay, so this is a vector on configuration space whose flow is just this, implements the diffeomorphism on the dynamical fields. So this d phi is now like the derivative operator in the phi a of x direction. So then we can rewrite this thing as in two different ways. We can also say it's the Lie derivative with respect to xc of phi a. So now this is a Lie derivative from the point of view of a space-time vector. This is from a configuration space vector, but they give you the same thing because I define the vector like this. And then in fact, we can also write this as xc dot delta phi a. Okay, all of those things are true. Now let me say more carefully what's the difference between this xc and this c here. So this thing is the thing that implements the diffeomorphism on dynamical fields because it's a configuration space vector. But this xc, it doesn't act on background fields. And so the key thing for being covariant is that whatever background fields are present have to be invariant under whatever diffeomorphism you're talking about, because if they're not, then they're not allowed to transform, because symmetries aren't allowed to act on background fields. So when we say that the Lagrangian is covariant, what we mean is that the Lie derivative of the Lagrangian with respect to xc is equal to the Lie derivative of the Lagrangian with respect to c. Okay, this is the definition of saying that the Lagrangian is covariant with respect to the diffeomorphism c. It's saying if you implement the diffeomorphism only on the dynamical fields, you get the same thing as if you had implemented the diffeomorphism on both dynamical and background fields. Okay, so now let me say how to find the Hamiltonian. So roughly speaking, right, we just want to find, given any diffeomorphism C, we want to find, so remember our formula before? We said that the x, the vector that gives the flow and phase space for the Hamiltonian, H, was given by omega inverse acting on a gradient of the Hamiltonian. Okay, so what that we can move the omega over to the other side, and we can write this as del H equals minus xh dot omega, where dot here indicates inserting a vector into the first argument of a differential form. And the minus sign comes because that put it into the first argument instead of the second argument. Now, if I want to say that I correctly got the Hamiltonian for some diffeomorphism, HC, then I want this equation to be true where this x is precisely this vector field here, which is the one that generates the diffeomorphism. So having correctly identifying the Hamiltonian means finding a function HC which obeys this, where here let me put pre-symplectic. Let me put the pre-symplectic form. So so the task of identifying the Hamiltonian is that you take this vector field here that implements the Lie derivative on all dynamical fields, you insert that into the pre-symplectic form that we just computed, and then you see if you can find a function HC such that this equation is true. This is how you determine the Hamiltonian. Now, I don't have time to go through the algebra, although it's in the paper. So the idea is using all the formulas that we just discussed, we just compute the right-hand side of this equation. So we have a formula for omega tilde, we have a formula for xc, we evaluate it, and when you evaluate it, lucky us, we find that indeed it is equal to the variation of something, to the phase space exterior derivative. So we find that hc, and the only thing we have to use in doing the derivation is that the Lagrangian and then also little l and c are covariant under the diffeomorphism that we're talking about. So then what we find is that we get an integral over a Cauchy slice where it won't matter which Cauchy slice we pick, something called jxc, which I'll explain in a minute, plus an integral over the boundary of the Cauchy slice of c dot little l minus xc dot c. So then let me just say this jxc is what's called the Euler Occurrence. So it's equal to xc dot theta minus c dot l. So let me unpack this a little bit. So remember, theta is a one form on configuration space. This is a vector on configuration space, so I can insert that vector into this one form. What that does is it takes delta phi everywhere and it replaces it by the Lie derivative of phi with respect to c. And then now here, L is a D-form on space-time, c is a space-time vector. So I insert this space-time vector into the first argument of the Lagrangian. Okay, that's the definition of this Euler current. And then similarly over here, I'm inserting the space-time vector c into the first argument of little l, and I'm inserting the configuration space vector xc into the first argument of the configuration space one form c here. Okay. So this formula is correct as long, again, the only assumption here is that the theory is covariant under c. Now, moreover, the theory is covariant not just under xc, but under arbitrary diffeomorphisms, then something better happens, right? Which is like general relativity, right? Like say there just aren't any background fields. So then it's shown in the paper of Iyer-Wald, again, I'm sorry I don't have time to show it now, that this jxc can actually be written as d of a d-2 form qc, which Wald calls the Euler charge. Now, calling it the Euler charge has got to be the dumbest thing I've ever heard. I have no idea why he called it the Euler charge. It doesn't generate the symmetry. A reasonable person would have called this QC the Euler potential or something. Okay, the Euler charge is the Hamiltonian, right? That's the generator of the symmetry. So in these generally covariant theories, you can then write HC. So now the great thing is that then this is the only term that's integrated over the bulk of the Cauchy surface. So if it's d of something, then now everything just lives on the boundary of the Cauchy surface. And we get qc plus c dot l minus xc dot c. Okay. And that's our formula for the Hamiltonian and covariant theories. Now, okay, I was going to explain this for general relativity, but since we're running out of time, I think I just want to make a few general comments instead. In general relativity, the only comment I'll make is that you can go and look in our paper, and you'll find the expressions for QC and C and L. And they're all fairly easy to figure out given the Einstein-Hilbert action. And you can check that if you substitute them into this formula, you get the ADM Hamiltonian. Now, I want to close, though, by comparing this. So since some of you maybe have studied these papers of Iyer and Wald. So Iyer and Wald, they had this term and this term, but they didn't have this term. So in general, their formula for the Hamiltonian is wrong. And the reason is because they did not realize that in the definition of the symplectic form, so I want to remind you this omega, right? I defined it to be the variation of theta minus dc. And the c here was the origin of the c there. So if you don't include this c in omega, then the symplectic form you get will not be conserved. So you have to include it. And I've actually discussed this with Wald, and up to philosophical things he agrees. So this term needs to be included. Without it, you don't get the right answer. And there are simple examples where it's clear you don't get the right
What
answer.
what are the philosophical differences?
Oh, well, okay. So Bob thinks, so the thing he doesn't like is that this C, it's covariant under diffeomorphisms that preserve the location of the boundary. I haven't told you what it is, but in general relativity, we can write it out. Well, maybe I will actually. Well, why don't I just write out what these things are? So to answer this, it's better to have the example on the board. So let me just quickly write. So for general relativity, L is 1/16 pi g times r minus 2 lambda times epsilon. Little l is 1/8 pi g times the extrinsic curvature times the boundary volume form. And then, let me see. So then theta plus delta L is equal to minus 1/16 pi g times k mu nu minus k gamma mu nu, epsilon of the boundary variation g mu nu plus dc, and c is equal to what I'll call little c dot epsilon partial m, where little c, mu is a vector, is minus 1/16 pi g gamma mu nu n alpha dg nu alpha. Okay. So let me so remember the name of the game here was that on the spatial boundary we wanted this to be a total derivative. So this term here is a total derivative with this c, but then there's this other term. So this term you may remember, it's the Brown-York tensor contracted with the variation of the metric on the boundary. So to get a good variational problem, you have to either choose Dirichlet boundary conditions where you set the pullback of the metric to be fixed. So like that's what we do in ADS CFT. Or you have to set the Brown-York tensor to 0, which is like Neumann boundary conditions for gravity. So after you impose either of those boundary conditions, you're just left with DC, and here's the C. Okay. Now, let me comment both on the Gibbons-Hawking term and on C. So these are quantities which are covariant under diffeomorphisms that preserve the boundary, right? Like the extrinsic curvature is a tensor under diffeomorphisms that preserve the location of the boundary, but it's not a tensor under diffeomorphisms that move the boundary. So another way of saying that is that this L, the Gibbons-Hawking term, it can't be covariantly extended into the interior, okay? And similarly, this C is covariant on the boundary. You know, I just constructed it out of boundary tensorial objects, but it's not covariant as you extend it into the interior. Now, Bob thinks that we shouldn't be allowed to add to the symplectic form things that are only covariant at the boundary, even if they're only a boundary term. He just thinks that that's offensive. Now, he didn't say that it's wrong. He just said that he thinks that any theory where you have to add something that can't be covariantly extended into the bulk to the symplectic form is a theory that is bad for some reason, and we shouldn't be allowed to discuss it. So in other words, he thinks that we should just legislate that only theories with C equals 0 should be allowed to be considered. I don't know what to say. I mean, he can choose to only consider the theories with C equals 0, but I don't think he has a good reason. It just, you know, offending his sense that everything should be covariant, I don't think is a good enough reason. I mean, I think it's covariant enough, honestly. It doesn't need to be more covariant. If they're only going to integrate it at the boundary, then let's say it's just covariant under the transformations that preserve the boundary. Okay? But he acknowledged that if you drop this philosophical principle, then you definitely have to include this term. Any other questions? I can be done here, so we can move to questions.
Well, if that's the case, then maybe we should thank Daniel, and then we can take some more.
We have a question.
Oh, Daniel, this is Eric.
Hi, Eric.
Yeah. So in the Iyer-Wald formalism, they had this additional term which they call delta B, whatever the B on the boundary. But I thought also that was not covariantly extendable.
Yeah, that's right. So that's why. So good. So let me. Good. So that's a. Thank you for making that point. So that term is this one here. So here. So in their paper, this B just kind of comes out of nowhere. They say, oh no. Basically, they say they want this to be true, but it isn't true. So we have to look for some boundary term we can add to make it true, right? And that's how they come up with this. But you see, I systematically got this out of the formalism by using this L. But you're absolutely right that this term does not extend covariantly into the bulk. Now, I'm just telling you what Bob says. I'm not trying to defend this. He thinks it's okay to have a term in the Hamiltonian that doesn't extend covariantly into the bulk, but he doesn't think that it's okay to have a term in the symplectic form that doesn't extend covariantly into the bulk. Why does he think that? I don't know. I couldn't understand. I mean, it seems like a silly point of view, honestly. But.
So when I look at that term, they didn't connect it directly to the Gibbons-Hawking boundary term. They really just said that it's some term that needs to satisfy a certain property, like that it's a variation basically of the symplectic potential.
Yeah, it's some kind of integrability requirement. So what I've basically done is I've built that integrability requirement into this equation that theta plus delta L is equal to dc. So then I get it for free by using this equation, because you see this kind of says that the variation of L is equal, right? It says, theta minus dc is equal to the variation of something. So then that gives me my B for free, and you can kind of see where the L is going to come in there.
But why didn't their term already include this last term that you said you added?
This one. Yeah, because they used the wrong symplectic form. So they tried to solve this equation, which has omega tilde in it. But my omega tilde was defined as, let me write it here. My omega tilde is the integral of the variation of theta minus dc, dc over a Cauchy slice. So they didn't include this term. So they solved this. So what they did was they solved this equation with the wrong symplectic form, and that's why they didn't get this term. And then for this term, they had to guess and check because when they computed this, they got something that wasn't obviously a variation. But that's because they didn't realize that you could use this. And that the Gibbons-Hawking term gives you that for free, or in general, the generalization of it, right? I mean, just this boundary term in the action always gives you that B. You never have to think about it.
All right.
So if you like, they assumed it, I derived it.
Hey, can you hear me?
Mm-hmm. What's up?
Okay. I guess I have one comment on that. I mean, they did write down this C type of term. They called it an ambiguity. And I think people...
No, but the whole point is it's not an ambiguity, right? So what they said, so Wald's religion is that you're never allowed to talk about boundary terms. So everything has to be ambiguous up to all possible boundary terms at every step of the calculation. And then whenever you get to the point where you just really need the boundary term, then you try to guess it by consistency. That's how they do things. But I think it's really, 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 really wrong to call it an ambiguity, because the boundary conditions are part of the theory. The boundary terms in the action are part of the theory. And you have to impose these conditions. So the only ambiguity that there is left is an ambiguity that contributes to nothing, right? So for example, like you could change the bulk Lagrangian by D of something, and then also change the boundary Lagrangian density to cancel the change that you made. So you're still allowed to do that. You're also still allowed to shift theta by a total derivative and then absorb that into C, okay? But all the formulas that count here, like for the Pre Symplectic Form or for the Hamiltonian, are going to be invariant under whether or not you do that. So they're not ambiguities. The Hamiltonian and the symplectic form are completely unambiguous.
Okay, I also had a question. When you were getting the Hamiltonian, was there a step that you needed to assume you had a boundary killing vector? Like if you,
Well, no, so what I had to assume was I had to assume that the boundary conditions were preserved by the diffeomorphism.
Okay.
So in some particular application, that might turn into what you said.
Okay, so I
think I assumed.
To get the Hamiltonian, there might just be special vectors on the boundary that have a Hamiltonian. Is that right? Otherwise, they just might not be actual.
Well, you need, so the only things I assume only two things. The first is that I assume that the boundary conditions are preserved by whichever diffeomorphism you're considering. And the second thing is that I assume that L and C are covariant under those, under the diffeomorphisms which preserve the boundary conditions. And so we gave some arguments about why we think that should be true. You know, if you start, basically, if you start with an L, which is covariant under C, and you want it to be a symmetry, then the little L kind of also has to be covariant. And then when you do the variation of the, so when you do the variation of big L, that's kind of going to have to give you a theta that's covariant. Actually, that's explained in Iyer-Wald. And by a similar argument, when you do the variation of little L, since theta is also covariant, DC is going to be covariant. And then if DC is covariant, well, C probably should be covariant too. It has even fewer derivatives. And those were the only assumptions. Yeah, other questions?
Hey, Dan.
Oh, hey, is it Jan de Boer?
Yeah, hi, greetings.
Hello.
I have horrible internet, so I didn't turn on the camera. I was wondering, maybe you said it, but the difference between having integral and non-integral charges is whether or not you can write the j psi as the d of a q.
Yeah, well, yeah, the question of whether the charge is integrated over space or only over the boundary of space. That was what that was related to.
Right. Does this formalism give you any new insight in the difference between those two different types of symmetries?
I would say that that was already well handled by Iyer-Wald. So basically, so if generically you don't expect the generator of this diffeomorphism to be a boundary term, right? Like in quantum field theory, the generator of time translation is the integral of T00 over space. And in this, so like you can check, for example, for the scalar field theory that this JC is just T00. And then these terms are 0 for the scalar, so then this is just the integral of T00 over space. So the only case where that doesn't happen is if the Lagrangian form is covariant under arbitrary diffeomorphisms, then there's this argument in Iyer-Wald that it has to be D of something. So that'll basically only be in gravitational theories, never anywhere else. You could say maybe in topological theories also, like Chern-Simons.
But I thought even in gravitational theories, there's diffeomorphisms that have an integral charge and ones that don't sometimes.
What do you mean by an integral charge? Maybe I'm confused.
Oh, and that you can integrate the charge. In other words, that you can actually find this just the difference whether or not you can define this Q or not, I guess.
No, but I can always, the procedure I just did can, oh, you mean, no, so the QC is there for any diffeomorphism whatsoever, because this is just in the bulk of the space, right? It doesn't care about the boundary conditions or whatever. As long as the Lagrangian form is covariant, this QC will exist. That was shown in the paper of Iyer-Wald. It's not obvious. You know, you have to do some manipulation using the general form of the Lagrangian. But they showed that you can always construct this QC.
Any other questions?
I have a further question about this C.
Yeah.
So what type of physical observable you can compute that distinguishes between two different choices of C?
Well, I would say C is in some sense not a choice, right? I mean, there's a, how shall I say this? Well, so C itself is not measurable. Because so if you look at the equation that defined theta, right, it was that the variation of L is equal to E plus EA delta phi A plus d theta. So that was the defining equation for theta, but it only defined theta up to a total derivative, right? Mm-hmm. So if I shift theta by dy, where y is anything, I get a theta that still obeys that equation. But if you look in this equation up here, you see if I shift theta by dy, then you can interpret that as changing c. So in fact, you can even set c equals 0 if you want to by shifting theta. But the thing is that if you want to set c equals to 0, you have to add theta d of something which is not covariant. And so if you do that, then theta won't be covariant. So I wanted to maintain the covariance of theta. It simplifies some calculations. Then you're stuck with this c. But other than this ambiguity, C is unique. Like there's no further choice of C. It's just you accept whatever the theory gives you.
Right. So to do like, for example, time evolution with the CFT Hamiltonian, that fixes a unique choice of C.
Oh, sorry. Are you talking about C or Xi?
C. Yeah. I mean, there's a C associated to time evolution, but I'm talking about C comes in the choice of the theory somehow, right?
Yeah. C is picked just by this. The only ambiguity in C is this ability to shift theta by d of something, but it has nothing to do with which diffeomorphism you pick. So I would say you just pick C once and for all. That's it. Like you fix this ambiguity however you like. I like to fix it by making theta covariant. And there's no further choice. I mean, you can do choices that change the theory, right? Like you can change the boundary conditions.
Right. That's how we should think about it. Right. Okay, thanks.
Mm-hmm. Any other questions?
Okay. If anybody has any other questions they want to ask now, then let's thank Daniel for this very interesting talk.
All right.